Hello, everyone. In the previous video, we introduced polar coordinates. Now, we saw that using regular Cartesian coordinates, this is sort of a rectangular coordinate system, right? The x component describes movement in a horizontal direction, and the y component describes movement in a vertical direction. Now, when we introduced polar coordinates, we saw that this is akin to using circles to define our coordinate frame. In fact, what you do is you define a radius and then you rotate that based on an angular component. Now, the goal for today's video is to describe how we can graph polar curves. And in particular, these are going to be very similar to what we saw for the parametrized curves a few lectures ago. And in this case, we're going to parameterize everything based on the angular variable theta. So you're going to have, as we saw in the previous video, maybe something like r is equal to a function of theta. Now, this is not easy. I'm going to offer that disclaimer up right now. And part of the reason why this isn't easy is because we are so used to working with Cartesian coordinates. But even someone like me who has worked with polar coordinates for a long time, I still have trouble with this stuff, and it is going to take some time. So I don't want you to get frustrated while we go through this, but I do want you to know that it will take a little bit of work with this stuff. Okay, let's start by trying to simplify a little bit of our analysis here by introducing some symmetries that we should take care of. So symmetries. Now, the first thing that we're going to do is we're going to see what happens when we negate certain variables. So what do I mean by that? Well, let's imagine we have a polar coordinate, let's say r comma theta. Then, as we know with this defines an angle theta right here of length r. And the question is, what happens if we negate the angular component theta? Well, that's going to put us down here. Why? Well, our radius is still the same. We're still the same distance away from the origin. But now our angle is going in the opposite direction. Remember, negative angles represent moving clockwise. So you're still in the same distance from the origin, you just rotated in the opposite direction. You could equivalently, based on all of these non-equivalent ways of writing our polar coordinates, this could equivalently be written like this. Okay, so it's just worth pointing out. But what really matters is what happens when you negate theta. Okay, let's look at another one. Let's see what happens when you negate theta and r at the same time. So in this case, let's start again with a polar coordinate. So let's say we have r theta right here. Then if you are going to negate r and theta at the same time, the first thing that you are doing is when you negate r, you take yourself from moving along the x-axis in the positive direction, and now you're moving along the x-axis in the negative direction. And then when you negate theta, you are rotating yourself backwards. So in this case, sort of upwards from the negative x-axis, by an angle of theta, so clockwise. Remember, that's what negative thetas represent. So in this case, you get a vector over here. So this would be minus r minus theta. So this is symmetry over the y-axis now. And the reason is exactly this, that angle down there is minus theta. Now, there's another way you could write this. You could say, or you can say that this is r and pi minus theta. So I'm going to leave that for you to think about on your own. What really matters is sort of minuses here. So maybe I should point this out. This is symmetry about the x-axis. X-axis. This is symmetry about the y-axis. And we're going to do one more symmetry here while we're talking about this. And this is going to be symmetry about the origin. So imagine again, we've got a polar curve or a point in polar coordinates described like this. So this is going to be r comma theta. Then if we just negate the r variable, not the theta variable, that is going to put us like this. And again, that comes from the fact that when you negate r, you're pointing in the y direction, and then still rotating is just going to bring your theta down. So this angle remains theta right here, and this is minus r comma theta. And in this case, this would be a symmetry about the origin. Okay, so this is sort of an akin to an odd symmetry that you would see in terms of even and odd functions. So let's summarize this. So since we are going to be interested in plotting curves, symmetries make things a little easier to plot because it reduces what we have to look at. So let's say the symmetry about x-axis. Symmetry about the x-axis, it says, well, if r theta lies on a graph, and here we're using the term graph as in sort of curves, any sort of curve through the xy plane, then the same thing, r minus theta lies on the graph. And so this is exactly coming from that picture that I have above, right? It's just saying that you can flip yourself over the x-axis. If you have r theta, you also have to have r minus theta. Okay, well, symmetry about y-axis. Y-axis here. Well, this is just having to do with this second picture here. We say if r theta lies on the graph, then minus r minus theta lies on the graph too. Okay, and obviously the last one has to do with my third picture. This is symmetry about the origin. So symmetry about the origin, that's sort of like this is my sort of akin to an odd symmetry for a function. So this says if r theta lies on the graph, then minus r theta lies on the graph. So, okay, so I'm presenting these to you, and it might be sort of hard for you to get your mind around, and that's okay. But let me do some examples where we can see this. Now, if you think about plotting curves, one of the things that matters when you're plotting these things is the derivative, right? So we're going to take a quick detour before we get completely into plotting these things. And we're going to talk about the derivative first, okay? So again, just like we did with parametrized curves, we're always interested in dy dx, right? So we're never interested in like the derivatives of r with respect to things like that. We just care about dy dx because that is the slope of the tangent line of these curves in the Cartesian plane. So let's imagine we're going to be given a polar curve. So this is the typical way that you get a polar curve. R, the radius, is defined in terms of the theta, the phase variable. So it's some function of the phase variable. So we saw examples of this. We saw that we can describe a circle centered at 0, 3 in the last video by r is equal to 6 sine theta, if I recall correctly. So this is the general type of curve we're going to look at. This is a parametrized curve. You can think of this as r is equal to f of t and theta is just equal to t. That's the same idea. And we want the slope of the tangent to the curve dy dx in the Cartesian plane. So, you know, the quick thing that people might do is they might just say, well, it's just f prime of theta. Well, no, right? Because this is, you know, the movement in r and theta. R is away from the axis. Theta is sort of angular. This is different than movement in the xy coordinate frame. And so therefore it has a different meaning. So we have to be very, very careful here. Well, what we're going to do is we're going to recall that x is equal to r cos theta, which is f of theta cos of theta. By our definition, r is equal to f of theta, and y is equal to r sine of theta, which is equal to f of theta sine of theta. Okay, and now what we want is we want dy by dx. So let's look at what this should be. Dy by dx is equal to, again, we're going to treat these things sort of like fractions. This is made rigorous using, you know, the chain rule for derivatives, but this is the same as the derivative of y with respect to theta divided by the derivative of x with respect to theta. So this is just like what we did with parametric curves. And now let's take a look at what this becomes. This is the derivative with respect to theta of f of theta sine theta divided by the derivative with respect to theta f of theta cos theta. Okay, so we have a quotient here, but we also have a product rule that we need to apply to take these derivatives. So this is going to be, I'm going to say f prime of theta. So the derivative of f with respect to theta times sine of theta. And then plus f of theta cos of theta. So that's just the derivative of the numerator here, divided by f prime of theta cos of theta minus f of theta sine of theta. So of course, this is a quotient. We always have to be careful of, you know, the dividing by zero. So this could possibly be a point of contingency here, but as long as that denominator is not zero, this is the derivative for the slope of a parametric polar curve. Okay, so it's complicated, and I can guarantee that the first time you look for the derivative, you're going to forget this formula, and you're going to get the wrong answer, and you're going to go why. Then you're going to have to look back at this and remind yourself, oh, it's not as simple as just taking a derivative with respect to theta of f. Right? It's a complex formula. It comes from the fact that every time, you know, when we define derivatives, when we define the slope of the tangent, these things are all for Cartesian coordinates. So we have to be careful. We have to convert back to Cartesian coordinates, then take some derivatives. Okay. So now that we have an idea of sort of what we're plotting here, I mean, you know, of slope and symmetry, now we can get into plotting. Sorry, I jumped the gun. So we're going to do 3 examples of plotting, and I'm going to show you the complexities that arise here. Right? As I said, this is not an easy thing. This is something that you need to take slow and be careful with. So let's say graph the curve. So graph the curve, r is equal to 1 minus cos of theta in the Cartesian. So the Cartesian xy plane. Okay, so think about what this is saying, first of all, right? It says for every angle you are from the origin, I can define, every angle from the positive x-axis, I can define a radius, how far away you are, right? So you can imagine yourself being rotated around by theta, and you're sort of tracing out the radius of how far you are from that thing. So, you know, you can imagine maybe like little flower petals or something like that. So the first thing that we want to do is we want to address which symmetries we have. So we're going to use our results from the previous page here. Let's look at symmetries. Well, in this case, we are symmetric about the x-axis. So why? Well, if we have r theta on the graph, so if we know this is a point on the graph in polar coordinates, this tells me that r is equal to 1 minus cos of theta, which I can use the fact that cosine is an even function, and this is the same as 1 minus cos of minus theta, right? For any theta, this is going to work because cos is an even function, which tells me similarly that r and minus theta obey this equation, and therefore they are on this graph too. On the graph. All right, so that's how you apply those symmetry arguments here. Now, what else do we know? We're gonna write down a lot of points here to try and get ourselves to understand this. So as theta increases from, say, 0 to pi, so this is going from the positive x-axis all the way around to the negative x-axis. Again, think of these things as circles. That means that cos theta, well, this thing is going to decrease from 1 to minus 1. And r equal to 1 minus cos of theta. Well, this thing increases from a minimum value at 0 to a maximum value at 2. Now, the first thing you're asking yourself is, Jason, why did you restrict yourself from 0 to pi? Well, from 0 to pi sweeps out the entire top half of the Cartesian plane, and I know that I have symmetry about the x-axis. So whatever happens at the top, then you can just mirror it over the x-axis by the symmetry. So I only really have to look from 0 to pi in this case, right? Okay, that's one nice thing. How about some slopes? So you can use the formula above to find that the curve leaves the origin, and that is r theta equal to 0, 0, right? So this is when theta is equal to 0, then r is equal to 0 on this curve with slope. So take it, put it into that formula. You're good at derivatives. You can do that formula above. Then it's going to be tan of theta is equal to 0. And returns with slope tan of 2 pi equal to 0 as well. So what does that mean? It means that, if you use these tangent curves to sort of map out you're sort of feeling in the dark around these true curves. Well, this thing sort of starts flat at 0. That's what this is saying. Okay, so just like what we did with the parametric curves, we're going to put in a little table of values here to see if that can help us a little bit. So let me move to the next page. I'm going to give you an angle, and we're going to figure out where we are on this curve in terms of polar coordinates. Again, don't lose sight of all this is saying. It's saying, depending on the angle that I am from the origin, how far away am I? That's the only thing that this is describing. Okay, so at angle 0, we've already seen that we are at the origin. Okay, how about pi over 3, for example? Well, in this case, you are going to be at r is equal to 1/2. So you can just put these into a calculator if you want to. When you are pointing straight up, then cos is 0, so you get r is equal to 1. You're 1 unit away from the origin. And when you're at 2 pi over 3, then you are at a distance of 3/2 from the origin. So you're getting farther from the origin now. And when you get all the way up to pi, we've already seen this, you're at 2. Now, it might take you a few more data points to try and round this thing out, and you are perfectly welcome to do that if that makes you more comfortable. I'm going to go ahead and plot this thing. So in this case, maybe let's extend that down a little bit. Again, I'm going to start with the top half of this thing. And like I said, we can just mirror it. So again, starting from the origin, we're sweeping around. And what's happening is, as we've discussed, you're getting further from the origin as you move from 0 to pi. So that means maybe let's put ourselves right around here. This is our point. This is, maybe it should be down a little bit more. We should emphasize that. Let's say an angle, at a distance of 1/2 and an angle of pi over 3. And then up here, you're at a distance of 1 and at an angle of pi over 2. And then at 2/3, maybe here. This is certainly going to be a sketch. You're at a distance of 3 over 2 and an angle of 2 pi over 3. And then finally, you're at a distance of 2 and an angle of pi. Now, this is going to be a very rough sketch, but this should be a little bit more of a spiral shape coming in. So it's not my best. I apologize to everyone for that. But similarly, on the bottom half of this, we should have the same thing. And in this case, the shape that you're tracing out is called a cardioid. So this is a cardioid. And in particular, what you can see near the origin here is if you sketch out the tangent lines to this thing, so if you just sort of sketch a few of them on here, maybe like this and like this and like this, you can see that you are perfectly flat at 0 and you come up and around. And also, you know, my drawing is not great. I highly recommend searching up what a cardioid looks like. But, you know, you can see this is not an easy process, right? It takes a lot of thinking. It takes a lot of work to be able to sketch these things. It's not as simple as the sort of intuition that we built up with the Cartesian plane. Okay, let's take a look at another example here. Let's say graph the curve. So graph the curve r squared is equal to 4 cos theta in the Cartesian plane. Or the Cartesian XY plane, right? Okay, so first of all, this is not given to us in the form r is equal to f of theta, right? It's r squared is equal to f of theta. So it's immediately an issue. But let's note a few things. So we require cos of theta to be positive for this to work. There's no way you're going to say something negative on the right-hand side of this equation is equal to something positive, because the left-hand side is a square. It's always positive. So what this means is that minus pi over 2 is less than or equal to theta, which is less than or equal to pi over 2. Okay, so I could equivalently say 0 is less than or equal to theta, which is less than or equal to pi over 2, or 3 pi over 2 is less than or equal to theta, which is less than or equal to pi over 2. It just depends on how you want to view your thetas. And a lot of the times it just comes down to what's the right definition, what's the right region for thetas for the job. And in this case, I want to allow negative values of theta just so that I can make this just one sweeping interview or interval, sorry. Now let's talk about symmetry. Well, In this case, first we have symmetric over the x-axis. So over the x-axis. What do we have here? Well, we can say that if r theta is on the graph, just like we did before, this gives us that r squared is equal to 4 cos theta. And the same thing, because we're using cosine, this is the same as r squared is equal to 4 cos minus theta, which tells us r minus theta is on the graph. Now, think about what this means, right? What do the negative values of theta mean for negative pi over 2 less than or equal to theta, which is less than or equal to pi over 2? That's going into the fourth quadrant of the xy plane. Now, because of this symmetry, again, I can just restrict myself to the first quadrant and just mirror, just like I did with that poorly drawn cardioid. Similarly, we have symmetry over the origin. And this comes from the square in the r term. So r theta on the graph. Well, again, this is r squared is equal to 4 cos theta, which is the same as minus r squared is equal to 4 cos of theta, which implies that minus r theta is on the graph. And you can actually see that you have symmetry over the y-axis too. And that just combines both of those two properties. So same as above. Actually, maybe it's more similar than the same, but you just exploit the fact that you have even functions in R and even functions in theta. So there's a lot of symmetry to this thing, right? That's great. Okay, so now the question is, how do we handle this thing? Again, it's not given to us in the terms of a proper curve. But since we've restricted ourselves to the theta variables where cosine is positive, then r squared is equal to 4 cos theta is the same as saying r is equal to plus or minus 2 root cos theta. Now we have to be careful, right? We have the plus or minus coming in here now. So again, what we can do is we can exploit all of these symmetries and we can just restrict ourselves to the first quadrant. If we can just deal with the first quadrant, then we can mirror over the y-axis to get the second quadrant, and then mirror over the x-axis to get the whole Cartesian plane. This is why symmetry is awesome, right? I have reduced 4 quadrants down to understanding 1. Okay, so really, we have the graph r is equal to plus or minus 2 square root of cos theta. And so let's see what we can do. Let's put together a table of values here. So we have theta, then I'm going to get cos theta, and then we'll do r is equal to plus or minus 2 root cos theta on this graph. So here, let's take a look. We have, say, 0 plus or minus pi over 6. Let's say plus or minus pi over 4. Oh, sorry. Plus or minus, let's do pi over 3. And let's do plus or minus pi over 2. So when cos is 0, when theta is 0, cos is 1. And in this case, we get plus or minus 2. Then pi over 6, this gives us root 3 over 2. You're going to have to do some approximating here. This is something like 1.9, plus or minus 1.9. So you can just toss these into a calculator. It's nothing too fancy. At pi over 4, you get 1 over the square root of 2. Toss it into a calculator. This is about 1.7. And from pi over 3, you get a half. This in a calculator, you're getting about 1.4. All right, because that's 2 over the square root of 2. And then at pi over 2, you're at 0. Okay, so now, what can we do with this? Can this help us? Well, of course, right? So we actually just need the positive angles, as I mentioned. Let me draw a big Cartesian plane here. And let's see what happens. Okay, so first of all, at 0, so theta equal to 0, that's pointing in the x direction. The positive value here is 2. So I'm somewhere up here, 2, 0. That's in Cartesian coordinates. I know that it looks like it's, sorry, that's in polar coordinates. I know it looks like it's in Cartesian coordinates. Okay, then at say pi over 6, I'm going to be maybe something like this, and I get 1.9. Again, this is approximate, so please, it's hard to write approximate in there. Maybe that little squiggle will make people feel better about this. Then let's do, say, pi over 4 in this case. So that's a complete right angle. We're somewhere up right around here. We're at a distance of about, say, 1.7, right? So our distance from the origin is going down in this case to pi over 4. And then we've got pi over 3. So that's somewhere around here. Again, somewhere around here, our distance from the origin is going down. So we've got approximately 1.4 here, pi over 3. And the last one is when you're pointing straight up at pi over 2, you are completely at the origin. And so what this is sweeping out, if you want to put in a few more terms, that's entirely up to you. But essentially what you're sweeping out here is a nice half circle. So this should be a perfect half circle. You know, we've seen my drawing skills before. It's not great. But this thing is now symmetric over the y-axis, right? So that means that I get another half circle up here. So let's try and draw that. And then this thing is symmetric over the x-axis. So I get the other half of this thing looking like that. That is not great. I apologize to everyone for my poor drawing skills. Now, my poor drawing skills should illustrate something to you. If I can do it, you can do it, right? The point is, as long as we get a feel for what this thing actually looks like. And essentially what you're seeing here is that it's drawing these two loops, these two perfect circles. Now, this is kind of weird, right? Because if you think about what was happening, theta was being restricted to the right half of this thing. But from the fact that we have r is equal to plus or minus here, the minus radial variables flip me over onto the other half of the Cartesian plane. So you might have thought, and maybe I did too, that this thing was only going to exist in the right half plane because I was letting theta go between minus pi over 2 and pi over 2. But that square on the r really complicates things, and it mirrors me into the second and third quadrants of the Cartesian plane here. All right, let's do one last example here. And I'm going to show you maybe an alternative method to using some of the more complicated, the tables that we've seen. I want to walk through a method that might help you just a little bit. So let's look at another example here. So let's say graph now this thing has a cool name, lemniscate. R squared is equal to sine of 2 theta in the Cartesian plane. Okay, so if we were doing this the way that we just did the last one, I'm going to say, okay, let theta be restricted, and then r is equal to plus or minus, blah blah blah, right? let's do this entirely with sketching. Instead of going through all of those steps from the previous example, let's sketch this, and I'm going to sketch it in a weird way. I am going to sketch it in the theta r squared plane. So I'm going to imagine that I'm letting theta vary, and to that end, r squared is determined by the value of theta. Okay, so this is really weird. All I'm trying to do is sketch the function. What is the radius squared as a function of theta? Okay, so what does this thing look like? Well, it's just a sine curve, right? Nothing too fancy. So let's say we've got the usual sine curve. Because of the 2 theta in there, this thing has period pi, right? So I'm only drawing it on 1 period. If you want to draw it on more, copy and paste it. But here's the thing, okay? So first of all, radius squared is never going to be negative, right? We don't deal with complex numbers here. That's not something that we take care of. So that means that this is gone. And this is because we have r squared, right? So we're going to try and do this graphically without going through all of the work that we did in the previous 2 examples. Okay, so then that means that r squared is equal to sine of 2 theta. Then we have that 0 is less than or equal to theta, which is less than or equal to pi. So that immediately tells us that we are going to restrict ourselves to this blue region of the theta values, because those are the only ones that are reasonable when we're talking about r squared. And this also tells us now that in the sine 2 theta, if this thing is positive, then we get, just like last time, the square root of sine of 2 theta. So r is equal to the square root of sine of 2 theta. So if we just remind ourselves, this thing goes all the way up to 1, and it goes all the way down to -1. Then what we can do is we can now start sketching r as a function of theta instead of r squared as a function of theta. So let's do that next. Okay, so here's theta again. And now be very, very careful. I have r as my vertical variable, not r squared. And so what happens? Well, okay, if I look at that curve, I can take the square root of it. It's still going to pretty much give me everything between 0 and 1, right? If I take the square root of the peak up here, that still just gives me 1. If I take the square root of the origin values here, or the roots, that still gives me 0, and everything else gets filled down in between. Then what I do is I take plus or minus that. I have 2 functions. So let's use the plus one first, okay? So let's go all the way up to pi over 2 again. So I have, say, pi over 2 right here. And I've got pi over here. Nothing exists between pi over 2 and pi. The only thing I have now, I exaggerated how tall it goes up, and it should look like a nice sort of sine curve again kind of thing. Again, not my best drawing, but the point is, I think you see what I'm getting at here. And so my lower curve is the -1. So this is r is equal to minus the square root of sine of 2 theta. And my upper curve is r is equal to the square root of sine of 2 theta. Okay. Now we're going to put this in the Cartesian plane. So how does this help us to sketch in the Cartesian plane? And again, sketch. That's the active word here, right? I know that I'm not a great drawer. The iPad makes it harder for me. But the point is, you know, my sketches may be bad, but they certainly help us to visualize these things a lot better than just looking at an equation. And so I want this to give you some confidence as well, right? You can do poor sketches and still get lots of information out of them. So the question is, you know, how do we use this? Well, theta is between 0 and pi over 2. So again, we're going to look in the first quadrant, right? Because that's where theta lies. And let's sort of sketch out what happens here. So when theta is equal to 0, r is equal to 0. So that means I'm starting at the origin. And if we just trace the curve, so take your finger and put it on the screen right now and trace out the top half of the curve here in the r and theta plane. So I realize that this looks like r1. It's not meant to look like that. That should be the r plane. So this is the r direction. But take a look at what that looks like. Okay, so what happens to r? R comes off of 0, gets far away at pi over 4, right in the middle. And then at pi over 4, the radius starts decreasing again. And so what does that mean in the Cartesian plane? It means you start at 0 and you sort of blow off of 0 and you get your maximal distance away when you're at a 45-degree angle here. And then you come back into the origin, right? So rotating yourself from angle theta, or sorry, the angle 0 to angle pi over 2, then r does a complete loop. It goes from 0 back to 0, and its maximal distance away from the origin is at pi over 4, a complete right angle here. What happens for the bottom curve, so the minus square root of sine 2 theta? Well, basically exactly the same thing. Remember, we saw when you negate r, you flip over the origin. So we flip into the third quadrant here, and so we get this curve right here. And again, this thing has its sort of minimal value or its greatest extent from the origin at, in this case, it would be pi over 4 as well, right? And this comes from the fact that you're negating all of the theta values between 0 and pi over 2. So you can get that bottom curve just by using symmetries. So you can start off just the way we did with the previous two examples. And you can say this thing has a symmetry over the origin. Let me just work in the top right quadrant. Then I'll induce the symmetries later. Or you can get that curve from the bottom half of my graph in the r theta plane, or the theta r plane. Okay. So what's the takeaway? Well, we have a new way of describing curves in the plane, right? We can do these things parametrically in terms of polar coordinates. So we're sort of uniting the things from the previous videos. And in this case, you're parametrizing how far you are from the origin, r, in terms of your angle from the positive x-axis. These things are not easy, right? I have tried to emphasize that many, many times. It takes a lot of work, right? And then we have a few tools at our disposal. First of all, we have symmetry considerations. Second of all, if you want to get a little more technical, we can calculate slopes of these things. And that can tell you sort of angles that curves are sort of on. And then we saw with the last example that you can do this sort of geometrically as well, using a lot of the intuition that you built up of sketching these functions already. And we saw in that case, we went from the theta r squared plane, where you get a nice little sine curve. We can rule out the negative values on that curve because we have an r squared. Then what we can do is we can move to the theta r plane. And then from the theta r plane, we can move to the xy plane. Again, not an easy process. It takes a lot of care and a lot of effort, but it is an awesome way to describe curves that were previously very, very difficult to describe in Cartesian coordinates. Whereas if you think about the curves that I wrote down in this class or in this lecture, they're all really simple, right? R squared is equal to sine of 2 theta. That's extremely simple to describe these sort of little bulbs that we saw that were described or that were sketched in the last example.